All right, let's dive into one of the biggest questions in all of tech. How do you actually design a system that can scale from like one user all the way up to millions? We're going to break it down step by step.
Okay, you're in an interview, and they hit you with it. Design a service for millions of users. It's that classic kind of terrifying question, right? But here's the secret. Nobody builds a system for millions of users all at once. The real trick is to build it by solving one bottleneck after another. And, the whole journey starts somewhere. Surprisingly simple.
Yeah, believe it or not, pretty much every massive system you can think of started right here. Just one single server, doing everything. I mean, it's simple, which is nice, but it has two, let's call them fatal flaws. First, if this one server goes down, your entire service is just gone. Poof. And second, as soon as users start flooding in, it is going to run out of juice, and fast.
So, how do we get more power? Well, we've got two basic choices. We can scale up or vertically, which just means making our one server a complete beast. More RAM, faster CPU, the whole 9 yards. It's simple, but it gets crazy expensive, and eventually you just can't make it any bigger. The real key to massive scale is scaling out or horizontally, which just means adding more servers, and that's the path we're going to take.
All right, so we're adding more servers. Easy enough, right? But that immediately creates our first big problem. How do we actually spread the user traffic between all these new servers, and what do we do when one of them, inevitably fails?
The answer to that is something called a load balancer. You can think of it like a traffic cop for your website. It sits right out in front of all your web servers, and its only job is to take all the incoming requests and spread them out evenly across the whole group. It makes sure no single server gets totally overwhelmed.
So let's see how this works in practice. A user's request comes in, and it hits the load balancer first. The load balancer then just picks one of the available servers and sends the request there. Now, let's say server 1 goes down. No problem. The load balancer sees that and just starts sending all the new traffic to server 2 instead. And just like that, our web tier can handle way more traffic, and it's got failover. It won't crash if one machine dies. Boom. First bottleneck solved.
Okay, so we fixed the web tier, but really we've just moved the problem. Now all of our web servers are just hammering this one single database. To fix that, we're going to use a really common technique called database replication, specifically using what's called a master-slave model.
So here's the clever part. All the writes, new posts, new users, anytime data is changed, they all go to one single master database. That master's job is to then copy all that new data over to several slave databases. Now, why is this so smart? Because most apps do way more reading of data than writing. So we can spread that massive read load across all those slave databases. This not only boosts our performance like crazy, but it also gives us multiple backup copies of our data. Pretty cool, right?
So our system is definitely getting more robust, it's more reliable, but to get the kind of speed we need for millions of users, we need a secret weapon. There's a technique that just completely changes the entire performance game.
See, even with all these fancy slave databases, we're still bumping up against a fundamental physical limit. We're reading data from a spinning disk or even a solid-state drive. And when you have millions of people all trying to read the same popular article or watch the same viral video at the same time, having to go to that disk for every single request it's too slow. It's a huge bottleneck.
And this brings us to caching. The idea is actually super simple. Why would we go all the way back to that slow disk for data that everyone is asking for? Instead, why don't we just keep a copy of it in a blazing fast layer of memory? But, when I say blazing fast, how much faster are we really talking about?
Okay, I want you to take a second and just really let these numbers sink in. Reading from main memory is measured in nanoseconds. Reading from a disk, that's measured in milliseconds. That is not a small difference. We are talking orders of magnitude, like a factor of 10,000 or even more. This is why caching isn't just some nice little optimization. It is a fundamental, game-changing leap in performance.
Okay, so let's plug this into our architecture. We put the cache layer right between our application and our database. And the flow is super simple now. Does the application need some data?
First, it checks the super-fast cache. If the data is there, we call that a cache hit. It comes back almost instantly. We only go all the way to the slow database if we absolutely have to on a cache miss. This takes a huge amount of pressure off our database and makes the whole system feel incredibly snappy. So, caching is an absolute game changer. But like everything in system design, it introduces a couple of new, kind of tricky problems. First, how do we make sure the data in our cache is up to date and not stale? And second, what happens when our cache itself gets so popular and so big that it needs its own cluster of servers? So, one of the biggest challenges is keeping the cache and the database in sync. When some data changes, what do you do with the copy and the cache? There are different strategies. Write-through, for example, is really safe. It writes to both the cache and the database at the same time, but it's slower. Write-back is way faster. It just writes to the cache and says, I'll update the database later. But if that cache server crashes before it gets a chance to write to the database, you lose that data. It's a classic trade-off, speed versus safety.
And this brings us to a potentially catastrophic problem. Let's say you have 4 cache servers. A really simple way to decide which server holds which piece of data is to use a basic math formula, right? Like a modulo operator. But look what happens if you lose one of those servers. Now you only have 3. The math completely changes for almost every single piece of data. All of a sudden, your application can't find anything in the cache. This unleashes what's called a cache miss storm, where every single request suddenly bypasses the cache and slams into your database all at once, which would probably bring your entire site crashing down.
Okay, the solution to this terrifying problem is a really clever algorithm called consistent hashing. Instead of that simple, brittle math formula, I want you to imagine something different. Picture a circle, like a clock face, and on this circle, we map out all the possible values. Then we place our servers at various points on that circle, and we place our data keys on the circle too.
And here's where the magic happens. To figure out which server stores a particular piece of data, you just find the data on the ring, and then you just walk clockwise until you hit the first server. Now watch what happens when a server disappears. All that happens is the data that used to belong to it now just belongs to the next server clockwise on the ring. Everything else, it stays exactly where it was. The disruption is incredibly minimal. This is the algorithm that allows massive cache clusters to scale up and down without falling apart.
Okay. We have built a really solid foundation. Our system is fast, it's resilient. But to handle truly massive global-scale traffic, we need to introduce a couple of final, really powerful ideas. These are the concepts that let us decouple our system and scale different parts of it independently.
So think about a shopping cart on an e-commerce site. In a stateful system, the information about your cart might live directly on the web server you first connected to. This is a huge scaling problem, because it means every single click you make has to go back to that one specific machine. A stateless architecture is way smarter. It takes your cart info and moves it out to a shared place, like a database or a cache. Now, any web server in our entire fleet can handle your request because they can all see your cart. This makes our web tier incredibly flexible and super easy to scale.
And finally, what about really slow tasks, like say, processing a video you just uploaded? You can't just make the user sit there and stare at a loading spinner for 10 minutes. The answer here is a message queue. What happens is the web server takes your request and immediately puts a job, like process this video, into a queue. Then it instantly tells you, yep, we got it, you can go do something else. Sometime later, a totally separate group of worker servers will come along, pick that job out of the queue, and do all the heavy lifting. This decoupling is absolutely key. If the workers are busy or even if they crash, the jobs just wait safely in the queue until someone is ready to handle them.
And here it is. This is the result of our entire journey. I mean, just look at how far we've come from that one little server. A request comes in, hits the load balancer, gets sent to any one of our stateless web servers. That server checks the cache for data, and if it's not there, it reads from one of our slave databases. And if there's a slow job to do, it just drops it into a message queue for later. Every single piece we've added solves a specific problem, and critically, each part can be scaled independently. This is the blueprint of a modern system built to handle millions.
So what we've really done here is more than just look at a diagram. We've learned a method. We took this huge, seemingly impossible problem, scaled to millions, and we broke it down into a logical sequence of smaller, totally solvable problems. And that, right there, is the absolute core skill of system design.
You know, these aren't just abstract diagrams on a screen. These are the exact patterns that power pretty much every app on your phone and every website you visit every day. This journey, from a single server to millions of users, it's really just a map of solved problems. And now you have that map. So the only question left is, what problem are you going to solve?